That's better, right? Good. Good morning, my name is Eoin Woods. The reason I'm here and talking to you this morning, apart from Thessaloniki being a lovely place, and I'm really excited to meet a new community, is that climate change is one of the most urgent and serious problems facing humanity, whatever Donald Trump says. The thing is, for years, I was aware of climate change, and I thought sustainability was important, and I was concerned about emissions. But for years I thought, well, obviously, I'll do my recycling, I'll take a few less flights, that's what it's all about. And that's because I worked in the software industry, right? We don't produce any emissions. Our stuff's entirely virtual. But in fact, it's quite difficult to measure anything with climate change. You don't really, you estimate it using complicated models. In reality, current estimates for our industry, which the climate scientists call ICT, Information Communications Technology, it's 2 to 4% of global emissions, which doesn't sound too bad, does it? Until you realize that aviation is 3%, and they're the bad guys. So what does that make us? People who should be thinking about this. The other problem we've got is that most industries are reducing their emissions and working really hard on it. They've got working groups and R&D, and they're sponsoring university research. And what are we doing? We're building data centers. We're building data centers like they're going out of fashion, mainly due to AI, but to be fair, not just through to AI, normal increasing demand for platforms like Google Cloud Platform or AWS also drive it. According to the IEA are big news in this area. They're the International Energy Authority. They do lots and lots of research because that's what they're paid to do. In 2024, data centers were 1.5% of global electricity use. In 2030, they reckon it could be 4.5%. So it depends on lots of parameters. You can't tell the future, but about 4.5%. What's that relative to countries? It's the size of a mid-sized a large actually developed European country like Germany. So that's the size of data centers. This problem isn't going away. And in fact, some companies who've taken emissions, sustainability really seriously for quite a long time seem to be getting worse. Microsoft's emissions went up 30% in 2023 and about 25% in 2024. And remember, those are rates of change. The 25% is not really getting better. It's getting worse more slowly, slightly. It's still not a very good news story. And if you do research in ICT sustainability, you'll quickly come across this graph. It's very famous. It's what's called a meta study. It's where people from Lancaster University looked at all the other people doing this research. They brought their research together. They tried to figure out how it all related to each other, and they drew this. This is called a meta graph. It shows all the studies. The detail doesn't matter. But which direction are all the lines going in? Yep. The wrong way, right? They're all going the wrong way. It doesn't really matter beyond that. They're all going the wrong way. By all means, go and find it. It's a very interesting article. There's a URL, but in summary, they're all going the wrong way. So who am I and why am I standing in front of you and on your Friday morning when you could be doing other things? My name is Eoin Woods, and I realise that's not obvious unless you're from Ireland. Is there anyone from Ireland or with an Irish parent? Sometimes I'll be in the strangest part of the world and somebody will go, yeah, I know how to pronounce your name, I'm from Dublin. But I'm originally from Belfast. If you leave the E off the front, pronounce the other letters. That's how you pronounce my first name. I'm an independent consultant. I've been doing that about a year, maybe a bit less. Before that, I spent about 10 years building products, many of which are actually still in use, which is, I think, gratifying and frightening. I then spent about 10 years working in large banking-style organizations. My area was capital markets, if you're in banking. And then I spent 10 years working for a company called Endava, digital software engineering, building systems for other people. And I've done the normal stuff most speakers have. I've written some books and some articles, etc., etc. So what we're going to do, we're going to just discuss green software concepts. It's not rocket science, but people use some jargon, just like in every field. So we'll just go over the jargon. And then if we're going to be designing these systems, this is all a bit gloomy, what could we actually do? And actually, there's quite a lot we can do. So let's look at some constructive, positive things we can do. This would not be a talk in 2025 if I didn't talk about AI. I'm not going to talk much about AI, actually, but I'm going to talk a little bit about how we could also think about minimizing climate impact from AI. And then we'll have a case study, just to try and bring it to life a bit. An example of one team who did some really interesting work. And then finally, I'd like you to be as excited about this as I am. So I'll give you some thoughts as to what you could do on Monday morning when you go back to the office. You're all very quiet. Is that okay? Is that what you were expecting? Yes? Yes? Make a noise? No? Okay. I'll try and make some jokes, but, I don't know. I'll try. I'll do my best, okay? You work with me and I'll do my best. Green software concepts. Right, what's this all about? So, first thing that really annoys me, everybody calls greenhouse gas emissions carbon. That's the least precise term you can have for them. There's no carbon involved. There's only carbon dioxide, which is not carbon. You can tell from the name. It's carbon and oxygen, isn't it? Fused together. Anyway, everyone talks about carbon. I try not to, partly because I know some climate scientists who get really annoyed if you call it carbon. But I try and call it greenhouse gas emissions. If I call it carbon, that's also what I mean. So how do greenhouse gases relate to software? In two ways. Firstly, there's the way that everyone forgets. There are things called embodied emissions. Embodied emissions are all of the greenhouse gases that have been emitted before we got anywhere near running a piece of software on a piece of hardware. Because in order to do that, we typically need a supply chain. For example, do you realize that you indirectly are huge consumers of concrete? You just have to trust me, you are. That's because most of your workload runs in data centers, and data centers are mainly made by pouring concrete. And concrete is one of the worst building materials from an emissions perspective. So there's supply chains, and there's steel, and there's trace minerals, and there's rare earths, and all this stuff that we need. Then there's building things, as well as making the concrete. The actual building of the data center produces emissions. And then there's hardware manufacture. So obviously that's everything from our huge servers that we might indirectly use on a cloud, through to servers that we're buying in our own data centers, network equipment that we tend to forget about, storage, which is also has embodied emissions, and in fact, the bit we all forget, end user devices. Indirectly, and we'll talk about this in a minute, we can accidentally trigger upgrades to end user devices, creating more embodied emissions. The other half of the equation is the bit most people talk about and think about, that's operational emissions. In the software area, and this is where we're very different to, say, logistics. Logistics have lots of operational emissions of different sorts. We've basically got one that's worth measuring, and that's the energy, the electricity that we use, turn into power to drive our devices. And we can make some choices there, typically. We can use electricity that came from burning coal, or we could use electricity that came from solar power. And obviously they have very, very different greenhouse gas footprints. Anywhere in the world where you are consuming electricity, the grid you're consuming from will have a different balance of inputs at any time. If you're in the Nordics, where they have a lot of hydropower, in general, it will be relatively low emission. If you're unlucky enough to be in Central Eastern Europe, you're probably going to have quite high emission because they don't have a lot of hydro, they're not yet very developed in solar and so on. But it varies over time because different countries and different grids swap electricity. So the mix is what defines the emissions associated with your electricity. And that's called your grid carbon intensity. I mention that because that's a jargon term that green software people throw around all the time. They call it grid intensity. And that's all they mean is, what's the mix of renewables versus fossil fuels used to create your electricity? So that's the landscape, really. We produce embodied emissions, completely invisible to us. We can be very unaware of them, but they're actually quite large. And we produce operational emissions, a little bit more obvious. That's from our electricity. It's also worth bearing in mind that embodied emissions as a percentage, these are not absolute, no, these are percentage graphs. Embodied emissions as a percentage are very different for different kinds of hardware, and that's because of how they're used. If you've got an iPhone, these are real figures from Dell and Apple. You can go and download them from their websites. An iPhone 14, I haven't updated it, but it's not very different. An iPhone 14, it's mainly embodied emissions. And that's because it doesn't use a huge amount of electricity. After all, it's optimized not to. But there are a lot of embodied emissions in building an iPhone, and also shipping it, I guess. So for an iPhone, you've got to think about the embodied emissions, not maybe so much the operational stuff. A server, on the other hand, if you've got a high-performance, high-compute server, anyone here involved in scientific computing? High-energy physics compute? So those servers are the most extreme example. Over their life cycle, it's nearly all operational. It's the electricity they're burning. Yes, they have embodied emissions, but they use so much power over the life of the device. In percentage terms, they're not actually all that interesting. And different devices, basically, the smaller, more personal the device, the more the embodied emissions, the more highly used, shared the device is, the more the operational emissions. So that's worth bearing in mind. We'll come back to that later. Hold that thought about mobiles in particular. And the operational emissions, as we've said, they are the electricity you're using. And they are defined, as you might guess, by the greenhouse gas intensity. Remember what we called that? It's called the grid intensity. The grid intensity of where you are and the time you're consuming the power. That's quite important because the intensity varies all the time. And it can be measured over a 24-hour period, but also weekly and monthly periods. In the UK, for example, you will not be surprised to hear we get a lot more solar power in the summer than the winter. We are surprisingly good at generating solar power, but we get just more of it in the summer, as an example. And then, of course, there's the amount of electricity you use, obviously. And that's two things, really. One, how much workload, we call that demand. How much workload do you want to perform? But secondly, how efficiently do you perform it? So you multiply all that together, and that tells you, conceptually, what your operational emissions are. And of course, we can actually do it practically. We can find the power of the machines, the amount of the machine we're using, etc., etc. So that's all a bit gloomy. The question is, what can we do? The answer is, there are lots of things we can do. There are design patterns, tactics. There are indeed tools, which I'll touch on tools. That's really another talk. But I'll touch on tools as we go. Today, we're really going to talk about principles and tactics. So that is, what can we do when we design our systems to make things better? The Green Software Foundation is an industry body. Lots of firms came together to create it. And it's quite influential in this area. And they present these slightly differently today, but they've got 6 principles to guide you to make your software more sustainable. One is, obviously, emit. They use carbon, by the way, not greenhouse gas. So I haven't reworded their principles. I don't like the use of carbon, but I'll use it for now. Emit the least amount of greenhouse gas possible. That's sort of obvious, but if you're not thinking about it, measuring it, and optimizing it, that's unlikely to happen, and that's the point they're making. And the second one is, which will contribute to that, use the least amount of energy that you can. And again, that's sort of obvious, but if we don't state it and think about it, we're unlikely to achieve it. Agreed? Then if you are going to use energy, do more work when your grid is cleaner, that is, that grid intensity is lower, and less when it's higher. And we'll see how we might think about doing that in a minute or two. The other thing is, do you remember operational emissions are only half, well, they're a percentage, of the equation? Make sure that we're thinking about how much embodied emissions, embodied carbon, that we're incurring. And that's across the entire system, not just your servers in your data centers, but network equipment, storage, and what was the other thing we mentioned? Consumer devices. Think about, are you causing embodied emissions in consumer devices? Fifth principle is what you measure. What you don't measure, you can't improve, obviously. If you don't know where you are, and you don't keep measuring, you don't know if things are getting better. And finally, the last principle is written in code. It doesn't really sound as if it means anything. Understand the mechanism of carbon reduction. What they mean is, and they're being very diplomatic, because some of their sponsors are some of the cloud vendors, there's two ways you can reduce your emissions. You can actually reduce your emissions, or you can pretend to reduce your emissions by paying somebody else money. And that's the whole murky field of carbon credits, which I'm not going to talk about very much because I could do 20 minutes on carbon credits. But let's just say that companies that have very low emissions sell certificates about their low emissions to other companies that have higher emissions. And the way that it works is that the company with the higher emissions can now claim to have lower emissions, and the company with lower emissions slightly higher. It's transfer via market forces. It's meant to be a great idea. Most people in green software think it's a terrible idea. However, some of the cloud vendors do quite a bit of this, which is why, as they were sponsoring, this principle was worded somewhat ambiguously. But that's what they mean is, just be conscious. If somebody's telling you that they've got an intensity of 32, is that because they're really emitting that much greenhouse gas? Or are they emitting twice that much and they've just bought the right to tell you that it's half the amount, which is kind of meaningless. So those are the principles. Let's look at a few tactics. Tactic one is very well known. You may have come across it. It's called demand shifting. We generally have flexibility over where and when we do at least some of our processing. For example, if you've got a data ingest pipeline and you're using public cloud, it often doesn't really matter where in the world it runs. So we can run batches at different times and in different places. Given that our energy grids vary in intensity, it sort of makes sense that if we could move our workload to a time when the local grid is less carbon intense, greener, or to another physical location where they've got lots of, for example, hydropower, we would lower our emissions. And both those are perfectly sensible tactics. The things, of course, is that every architectural decision's got a trade-off, right? And this one, of course, this can be quite complex, especially if you move stuff around dynamically, which some people try to do. That's very complicated. There's also hidden emissions. If you have to move a petabyte of data to another region, that's going to involve quite a lot of emissions. So if you're saving X and your data movement costs X times 2, net, you're actually worse than you were before. Although you're probably feeling better because you think you've reduced your emissions, but actually there were hidden emissions you didn't think about. And the other thing, which is maybe an edge case, but you've got to be careful about not accidentally driving cloud vendor behavior by moving a lot of workload temporarily, which they misinterpret as long-term demand, and they go and build a data center for you. And a data center involves massive amounts of embodied emissions. That's the first tactic. Second tactic, which is a bit trickier in many cases, is demand shaping. This is about saying, well, we've got a certain amount of work to do, but at different times we can probably do different work or different intensity of work. For example, if we've got a heavily mathematical system in finance, there's a lot of calculation systems that I used to work on, for example, for risk. There are different levels of precision we can operate the risk at. We can do full calculations or sampled calculations. We can use more precision, less precision, and that uses more processing power and less processing power. We can, for example, use lower fidelity graphics. We can simply switch off some features if they've got very high carbon intensity. And the grid varies across time, right? So this is a real graph, by the way. This is the UK on a specific day. This is actual real UK grid data, which I extracted and shoved in Excel. So this isn't imaginary. It really does vary that much. It was in September, I think. So we could do quite a lot in the early hours of the morning when the grid intensity is low. For example, there's lots of wind or tide power. And then as the grid becomes less green, because lots of people are boiling their kettles, so they're switching on fossil fuel power stations, we might do less. Middle of the day, we might just have to do the work because it needs to be done, and we accept that. And then towards the end of the day, when suddenly everybody goes home, makes their evening meal and starts watching television, boiling their kettles, again, we kind of bring it down again. And then we ramp it up overnight again because it's relatively low intensity. Again, this adds quite a lot of complexity to your system. The other problem is that whenever I've had these conversations with people, I find this one a bit tricky because actually people don't really like the thought of varying their, for example, calculation precision to achieve better emissions. A few people sometimes do, but it's quite common they don't. So by all means, have that conversation, but that's my warning. It may be a bit tricky. Tactic 3 is move work to client devices. What did we say about client devices? They're mainly about embodied emissions, and the reason is they're idle most of the time. If you have one of those sort of system utility things on your mobile phone and you look at it, you'll notice the CPU usage is low nearly all the time, yet it's sitting there with its embodied emissions, and it is using power the whole time, just to stay alive, handle its interrupts, handle the network and all of that. That means that actually we'll get nearly no more emissions by moving suitable workload onto the client devices, and yet we'll free up capacity on the server devices, either needing less of them, that will be ideal, because that reduces embodied emissions and operational emissions, or if we can't get rid of hardware, we can reduce the load on it, so perhaps temporarily, at high grid times, causing it to use less power. So for example, you might not do all the processing of result sets on the server. You might move that to the client. You might cache a lot more data on the client so that it can minimize what it needs from the servers. You might move a resilience mechanism. So typically we do all the resilience on the server side, inside the data center and the cloud. You might think about moving some of that to the client, making a smart client that's got the resilience built into the mobile app. Again, there are some trade-offs. There's complexity. It's probably simpler to do it on the server side. That's why we do it there. You're also, I realize you're dependent then on the client device. And of course, we don't control the client device in many cases, except inside a company. That can be a bit of a problem. And there can be security and data movement problems. The dependency on the client device, of course, has a potential implication. What we absolutely mustn't do is move so much processing to the client device that we accidentally persuade people to go and buy a new client device, a new mobile, before they would have otherwise. Because obviously, most of it's about the embodied emissions. So we don't want them buying a new one early, because suddenly that's a load more embodied emissions. So we can demand shift, we can demand shape, we can move to client devices. We can also just measure. And actually, this is really important. Until we start measuring, we don't really know if we're getting better or worse at all. So emissions measurement is quite difficult, and it's all via estimation. I don't pretend that this is something you can simply flip a switch on the edge of your cloud platform and start measuring its emissions. You can't. But even estimates help us to motivate ourselves and direct action in the right direction. There are cloud vendor dashboards, and they provide some assistance. They're not perfect. All three major cloud vendors have one. GCP's carbon footprint device, AWS's customer cloud footprint something service. Azure's got several called emissions estimators and emissions calculators. Just one tip with them. Do you remember we said people can seemingly reduce their emissions with the application of money? Well, a number of these cloud dashboards did exactly that in the early days. I think now, definitely AWS very recently announced that they can now report proper location-based emissions through the dashboard. That's been about 3 years coming. I've been giving this talk about 3 years, and it's only just now that they can do that. GCP have always done it, but it's an option. You've got to make sure you switch it on. And Azure, last time I looked, didn't do it, but it's a bit ambiguous. So actually, I would need to go and do more research. But you could perhaps, nothing moves a cloud vendor like clients asking for it and threatening to move their workload. And that's undoubtedly why AWS have done it. So on your cloud vendors, if you can't see the emissions data you want to see, tell them, and tell them that you need it to be better. There is an open source alternative too called Cloud Carbon Footprint, CCF. Actually, I'm not sure the status of that, because having looked at it recently, it doesn't appear to have had many updates recently, but the idea behind it was it provided an open source version of the same thing. It sucked all your usage data up and then provided you with an emissions dashboard. You can also get raw data, and you can get various estimates from a number of vendors, including electricity maps, which is free of charge. You can do it on your mobiles right now. And What Time and Climatique. They're commercial vendors. They'll sell you data, but also they have basic introductory tiers, which are completely for free to get you started. And there's quite a few other tactics people talk about. It's sort of switch off your test environments so you don't need them, cache your static data, compress big data sets, age data so that you remove old data or you put it on cheaper storage, which is also lower carbon intensity. Basically, all of this is do less. And that's actually the sort of mindset in technology we need to have. We've always had this embarrassment of abundance. We've always had more resources than we've needed. We just need to be thinking slightly the other way, so that we're thinking, how do we minimize, while still doing our jobs, how do we minimize the compute resources that we're using? So how about AI then? Sustainability for AI is a hot topic which appears to be not going very fast. Everyone's talking about it, and yet we keep on basically building more data centers and putting more extremely power-hungry NVIDIA GPUs into them. As you know, AI-based systems, and I'm really talking about LLMs here, but actually anything that involves building a large model, even a really big classifier, involves huge amounts of computing resources. The processors, the storage, and the memory. And they also, in fact, do quite a bit of networking as a side effect, but it's mainly processor storage and memory. It is no surprise, then, that they're an utter sustainability disaster. Microsoft admitted in 2024, when they had to report this very large increase in emissions, and a number of shareholders had extremely difficult questions for them about one of the reasons we're invested in you is you seem to take climate seriously. Microsoft had to admit, well, we didn't see AI coming, it's now here, we just have to react to it. And so that 30% was largely due to AI workloads. The key determinants, if you're involved in AI, you're probably aware of this, is that the model size and the amount of training that it needs, and then the amount of inference, which, as you know, is the AI term for querying. When you run something in ChatGPT, that's inference through the model. Those three are the determinants. If you can reduce the size of the model, if you can reduce the amount of training needed, and if you can either make inference more efficient or do less of it, that's what will reduce the amount of compute needed, and reducing the amount of compute needed will reduce the emissions, which is the point. It's worth looking at the AI life cycle to see where the kind of things we've talked about already, which are sort of obvious, where you apply them to, say, a digital system like ticket booking, where they fit in AI. This model is called CRISP, which, I kid you not, I'm going to read it because I always get it wrong. The Cross-Industry Standard Process for the Development of Machine Learning Applications with Quality Assurance. You might not be surprised to hear it's a German standard. It's a very precise name. And it's like the SDLC, but for AI-based systems. And they start with understanding the business and understanding your data, as you know, preparing your data, doing your modeling, evaluating how effective your model is, deploying and using, then monitoring and maintenance. By monitoring and maintenance, they really mean how effective the model is. Is the model drifting? Has it shown bias? And then you go back to understanding your data again, and round you go again. So that's their life cycle for how you develop really AI models, but they would describe it as AI systems. So how do we improve this? Given that AI is a bit of a sustainability disaster, how could people following this kind of life cycle improve things? First thing is, when they're thinking about business and data understanding, they could start thinking about their emissions. They could say, well, we need a certain degree of performance, we need a certain degree of accuracy, and we need a certain degree of scalability of the model, we need a certain data set coverage, and they stop. Well, they could also say, and we need to limit emissions to a certain reasonable degree, and we need to monitor them and reduce them over time. So it could become part of the requirements process. When they're doing data preparation, actually, a show of hands, anyone here work in AI and training models? No, oh, no one, okay. I'm sure many of you use AI-based systems, yeah? In your system, or you use chatbots, or you use developer assistants. So these are the people generating those tools for you. So when they're doing data preparation, perhaps use an existing data set. These people tend to love going and finding a new data set, which is quite compute intensive. So minimize the collection, minimize the amount you have to store, use the smallest set you can, and minimize how much processing you do on it, because all of that is compute and storage. When you're creating models, perhaps think about starting with an existing model. Of course, sites like Hugging Face, that's what they're there for. Hugging Face is to models what GitHub is to code. If you want to find a model to reuse or a model to tune further, Hugging Face has got, I don't know how many, but I think it's hundreds of thousands now. So consider a model that's already been pre-trained. Maybe you can avoid all of those emissions. Use the smallest model you can. That kind of goes against today's general approach, which is, because they're language models, create the biggest you can. And what's the problem with that? Well, more emissions to store the thing, more emissions to train the thing, and more emissions just to ask it a question, more emissions for inference. Use the smallest model you can. Think if you, there are techniques like quantization, you can shrink the model. That's where you represent all of those weights and biases in smaller numbers with a bit less precision. See if you can do your training in the cleanest possible compute. So that might be a different time of day, might be a different region. And if you can, use specialized hardware. Now there's a trade-off there, because if you buy a load of specialized hardware, obviously it has embodied emissions. But often the specialized hardware is a lot more efficient. You use a lot less energy. When you're evaluating models, think, actually, could we get away, experiment, could we shrink the precision of this model or reduce the size of it and still get acceptable results? Because that's a big win when we deploy it. And when we deploy it, let's put it somewhere where the emissions are going to be the lowest they can be. Maybe we have to have it in our country, but let's find if there's a way of deploying it or using it somewhere where we minimize the emissions. And then finally, when they talk about monitoring, as I say, they're really talking about monitoring characteristics of the model, which is fine. But why don't we also monitor our greenhouse gas emissions and then try and achieve reductions in those emissions? So there's a lot, actually. We don't need to be fatalistic about AI. There's a lot we can do to improve the emissions profile, particularly the growth of emissions coming from AI. Okay, how might this look then for a real project? This is a real project, or was a real project, so been over a while. This case study is how you can demand shift. When we said demand shifting, that's where we move the workload. We move the workload in accordance, trying to find the lowest emissions impact for that workload. This is a machine learning project. You will not be surprised to hear there's a lot of them around. As we know, machine learning workloads, they're really resource intensive, so they tend to produce a lot of emissions. This team was very aware of that. It was a team in a company I used to work for. We were working with a client. The client was quite aware of their sustainability footprint. And they were thinking, well, we're running large machine learning batches. It was quite a batchy-based system. This is mainly about training. And they went, we'd really like to minimize the greenhouse gas emissions if we could. They had a particular workload they decided to start with, and that was classifying written Japanese script called Hiragana, if you speak Japanese. And the important thing was, it's a well-defined alphabet, but it's quite intensive machine learning because we're using graphical processing to spot particular elements in a character set. Typically, one training run of this, one classification run of this, tended to take about 10 minutes, but it was required many times a day. Even in the proof of concept, they were running tens a day. In the long term, they could have been running hundreds to thousands a day. So the individual batch is not very long, but there's a lot of them. So there's a lot of compute. And they're running on cloud because they needed bursty scalability, because sometimes there'd be a lot of backlog, sometimes there wouldn't be so much. They started actually trying to do some measurements, and they worked with a cloud vendor. They did some estimation themselves, and they worked with a cloud vendor. And on a specific day, they're in Western Europe, this particular client, running it in the evening, when we tend to encourage people to move workloads into the evening. If we ran in the evening, then we would have emissions of 125 grams of CO2 equivalent. That's the sort of jargon term. It's an estimate for greenhouse gas. So 125 grams at that particular time. So quite a lot, considering we've done quite a small bit of work. Then if they moved the region, they could save 25%. And if they moved it a bit in time, they discovered they could save about another 15%. So actually, they could nearly halve their emissions without changing their workload at all. They're not quantizing their model, they're not reducing their precision, they're not changing their language or their optimization, it's just moving workload around. They could nearly halve their emissions. So, as the team and the client said, we should do that. So they built quite a specialist little system, really, which is a machine learning pipeline. It was running on Azure. And the key thing about the machine learning pipeline was they built a mechanism, which, yeah, I'll skip the detail because we don't have that much time, but they built a mechanism where they had they could access the storage from different places, and they could move the workload into different locations. And they could do that programmatically. That wasn't a human being. They simply switched the workload. So they effectively, they ran the code in one place, or they ran it in another place. What they did was that they used the electricity maps service. I mentioned them earlier. They're the people who I got the multicolored European maps from. And you can do that yourself now. They're electricitymaps.com, I think. They have both a web UI, where they can show you in real time or historically what the grid intensity is like, or they've got an API. And you can say, for this point in time 3 weeks ago, what was the grid intensity in Norway? Or you can say, right now, what is the grid intensity in Greece? And they'll tell you. So as the pipeline ran, they used an Azure function to go off, as it happens via a GSF, bit of open source software to make it a bit simpler, to extract the current intensity and put it in a database. So they both knew what the grid intensity now was, but also over time they were building up enough data that they could get an idea of what the grid intensities tended to be at different times of day in the regions they cared about. The client liked the idea of deferring workload until it was needed, but pointed out that sometimes they needed to just get all of the workload. So they also, to be practical, they kept in a feature that allowed them to urgently schedule something, and that just ignored all of the grid intensity and just ran the job. They still stored the intensity information, though, so they knew what the implications were. And then, as the workload ran, they used a piece of open source software called the Green Metrics tool. What the Green Metrics tool does is it wraps your software in a little, very, very simple wrapper. It collects all of your resource usage and stores that in what it calls its consumption metrics database. And then it combines that. You give it access to your grid carbon intensity, and it combines the two to try and assess what your likely emissions would be, or either in the future or would be now, as you're running. So it gives you an estimate, and all of this is estimation. It's not accurate measurement, it simply cannot be, but it is a reasonably useful estimate. And so what they've done is they could have just built the machine learning pipeline in the middle with a scheduler and a single region. But by allowing themselves access to multiple regions and having access to the grid carbon intensity and collecting their usage stats and using Green Metrics tool, they've got a step in the pipeline where they run the Green Metrics tool and they across the two regions, and they say, which is the lower? And then, of course, if it's like a tiny, tiny difference, they just go ahead and run on the current region. But if it's a significant difference, they swap the workload to the other region. So what they managed to achieve in a team of actually perhaps a surprising number of skills required. They had business analyst involved, they had a solution architect involved, they had obviously somebody from the client, they had some developers and some data scientists. The data scientists were the ones who actually had the workload. They were the key people wanting to get stuff done. And they also had a couple of what today we might call DevOps engineers. So they were experts on pipeline building in Azure. And so it's a kind of cross-functional team. So a fair number of people involved, mainly part-time. But what they managed to build without a huge amount of experience and without involving any particular vendor or magic piece of tooling, was automatic demand shifting, both by time. They would sometimes delay the job because it was high intensity at the moment, or they moved it between regions, but they kept a manual bypass. That's quite important. That's a pragmatic thing, is sometimes you just need to do it. So they kept a manual bypass if it was urgent. The way they were able to do that was they got near real-time data collection from electricity maps to allow them to understand the implications of running in region A or region B now. And that was the key enabler. They also built a bit of predictive stuff because they had the database of the stuff they'd looked at before. But the key thing really was they could ask electricity maps, what's the current intensity in Greece? What's the current intensity in, say, the Netherlands? Therefore, we can pick the right one. And they actually, they actually estimated, estimated their electricity usage via Green Metrics tool. And Green Metrics tool is well worth a look as a way of starting out in this if you'd like to. It's not super complicated, you could write your own, but it's a really good building block. So then, suppose I have interested you enough, I hope, in sustainability and convinced you that software is part of the answer. What could you start doing to get your colleagues interested and actually start doing this on your projects? Well, the key thing is, don't start, as some people seem to try and do, by trying to rewrite all your Python in Rust. That's not the place to start. But because of one particular, quite old academic paper, there's been a lot of this floating around LinkedIn, that you should rewrite all of your interpreted code in compiled code. Don't start there. That's exactly the wrong end, as you'll see. The place to start actually is simply learn more, become informed. It's quite a complicated, nuanced field. It's worth learning a bit about environmental science at a sort of layperson's level. It's definitely worth understanding where the emissions come from for software systems in general and yours in particular, because different domains are different. Back in May, I spent a fascinating 2 days with computational physicists in Germany. They take this very seriously. I mean, they're physicists after all. And actually, they are working at such scale, these people are all part of CERN's distributed compute network, where I think the number is they can bring 650,000 CPUs or GPUs online into a single experiment calculation almost instantly. That's the scale they work at. And so for them, like embodied emissions is really important because they buy so many computers every year. Your environment, perhaps it's all about operational emissions. Or in fact, perhaps it is about embodied emissions. And think about your whole system. So there's quite a bit to start thinking about. None of it's rocket science, but there's a bit to go and learn, to get on that journey. There's a few good books, there's some free training, I'm sure there's commercial training as well, and there's a number of organizations who publish lots of useful stuff on their websites. So just start by figuring it out. And then do less. That's actually the simplest thing to do. If you look across your technology estate, whether you're a high-performance SaaS vendor, whether you're from a national broadcaster, whether you're from a bank, whether you're from somebody who's developing specialist apps for a very narrow industry, you're probably going to find you're doing more than you need to. You can probably think now about things, old storage, communication stuff you don't need to do, perhaps compute that isn't really very, very necessary, test environments that are left on the whole time just because it's sort of simpler. All of that stuff, just do less. Use less hardware, directly or indirectly, use less energy. And then, once it's good to fundamentally use less energy, it's then the third step is let's get energy aware. What's the grid carbon intensity of the energy you're using? In other words, given you've already thought about how much energy am I using, what's the environmental impact of using that much energy, and could I think about putting pressure on someone or moving my workload or whatever it is to use low-intensity electricity. And that's not typically very complicated. In most countries, there are sources of renewable energy available. I'm sure in Greece, solar must be massive, and also I imagine tidal because of your immense coastline and strong tides, same as in the UK. And the other thing is, if you're using cloud, who here uses public cloud for their systems, just as a matter of interest? Yeah, not that many actually, but those of you who are, go and learn about your public cloud's greenhouse gas efficiency. They all publish it, but they don't publish it very visibly. You may need to go and search for it, but the information's all there. And those of you who aren't on cloud, you can be talking to your organizations about where are our data centers and where do we get the electricity for them. And many sustainability groups in big companies are very, very happy to have that conversation because it's something they're thinking about too. Once you've done all that, we haven't changed a line of code at this stage, but we've actually probably had quite a big impact. Switching stuff off might involve some infrastructure changes. Maybe we do infrastructure as code for the test environment, so we can switch it on and off again. But we haven't really changed the system. We can then start thinking about what, at the architecture level, because that's normally where the impact is, at the architecture level, what can we do? So we could look at some of these GSF patterns. Some of the tactics I talked about earlier, they started life with the Green Software Foundation. Just one thing to be aware of. You're all experienced designers, developers, architects. What's the question, or what's the answer that you always give to somebody when they say, how about this? You always say, it depends, don't you? Because it does. And actually, those GSF patterns, I do see one danger with them is they don't always work. They're not always very clear about some of the trade-offs. When you can all think through the trade-offs, you're all great designers. You're at an event like this. So learn about the GSF patterns and then think them through. In my environment, is this likely to actually produce a better outcome? And do some measurement. Perhaps you could prototype it. And then finally, should you have learnt more, done less, used clean electricity, and then found a couple of strategic changes you can make to your system, then you might think about optimizing some code. Because a lot of people want to start at this end, because frankly, rewriting some old Python in Rust looks quite fun. The problem is, starting with code optimization, you often don't know if you're having an impact. If you are having an impact, you would be surprised how little, for many systems, how small the impact of rewriting the code is. Because as you know, a lot of our code in mainstream systems is not compute bound. It's storage bound and network bound and memory bound. So yes, you could rewrite it in Rust and it'll be 50% fast, it'll be 50% more efficient, and actually it'll make almost no difference because it spends most of its time waiting for the database to do something. So by all means, look at code optimization, but work out, is it really going to pay back? So I said learning more. Very good book to start with is Building Green Software by Anne Curry, Sarah Sue, and Sarah Bergman. There's also a nice one written on an independent basis by just a software developer who feels very strongly about this. I like his book because I don't agree with everything in it, but he's got strong opinions and it's very actionable. He sort of tells you what he thinks you should do. And at the bottom, the Linux Foundation has got free training, which you can repeat as often as you want, and you can get a free certification from it as well. And there's some organizations on the right-hand side. Just go and look at their websites, particularly start maybe with the GSF. And also climateaction.tech. GSF's quite corporate. Climateaction.tech is very grassroots. If you're not into quite the corporate stuff, climateaction.tech is all done on Slack. You might prefer that. And then there are some resources you can kind of go and look up, standards and data sources in particular. So, thank you very much. I hope I've raised the interest in green software, and perhaps you could go back on Monday and start thinking about how you understand and reduce the emissions of your software systems. Thanks for listening.
Are there any questions that you want to ask Mr. Woods? No one?
I will be around until tomorrow lunchtime if you want to grab me in a break.
All right. Thank you very much, Mr. Woods.